Hello, everyone, and welcome to Aviation Physics. I am Dr. Chen. Go Dolphins! Today, we're going to get into the absolute bedrock of everything we study in this course Newton's law of motion. You simply cannot understand how an aircraft flies, how a satellite orbits, or how a rocket gets off the ground without a solid grasp of those three fundamental laws. Everything from calculating takeoff distance to understand lift and drag comes back to the principles laid down by, say, Isaac Newton over 300 years ago. Let's start with forces. And let's start with the man himself, Isaac Newton, born the same year as Galileo dies. His contribution to science are almost impossible to overstate. We are talking about the laws of motion, the law of universal gravitation, foundational work in optics, and he even invented calculus, seemingly in his spare time. He is without a doubt one of the most influential scientists in the history. And for us as aspiring pilots, engineers, and physicists, his work is our starting point. Before Newton, our understanding of motion was heavily influenced by Aristotle, who believed that an object's natural state was to be at rest. This feels like common sense, right? If you push a book across a table, it stops when you stop pushing. Aristotle would see motion requires a constant force. But Newton, building on the work of Galileo, presented a revolutionary idea in his masterpiece, the Principia Mathematica. He proposed that it's not the motion that requires a force, but a change in motion. This is the key insight that changes everything. So let's define our terms. What is a force? You can imagine a force as a push or a pull on some object. For example, when a tennis ball is hit with a racket, the player can hit the ball at different speeds and direction, direct it into different parts of the opponent's court. The applied force has magnitude and direction, so force is a vector quantity, just like velocity and acceleration. In aviation, we're obsessed with forces. We have the four fundamental forces of flight: thrust, drag, lift, weight. At its simplest, a force is a push or a pull. It always acts on an object. It always has an agent causing it. And critically, it's a vector. This means it has both magnitude and direction, which is hugely important. Forces can be contact force, like the friction from runway or the drag from the air moving over the fuselage. Or they can be non-range forces, with the most important one for us being gravity, which creates the aircraft's weight. As a brief summary, this table provides a few of the essential facts about those five forces we have explored as specific example. The known fundamental forces in nature are all field forces. These are in order of strength: the strong nuclear force between subatomic particles, the electromagnetic force between electric charges, the weak nuclear force, which is responsible for radioactive decay processes, and the gravitational force between objects. The gravitational force is a mutual force of attraction between any two objects in the universe. Even though the gravitational force can be very strong between very large objects, is the weakest of the fundamental forces. Let's see just how weak gravity is. Imagine rubbing a balloon in your hair, which gives the balloon a tiny electric charge. Because of electric force, the balloon will stick to the wall and resist the gravitational pull of the entire Earth. The gravitational force is given by this equation. Gravitational force equals gravitational constant G, which is given by this number, the mass of two objects, and r squared, where r the distance between those two objects. The magnitude of the gravitational force acting on an object of m is called the weight. W of the object, given by the equation as shown. Weight equals mg, where g is the acceleration of the gravity. On the surface of the Earth, weight is calculated from the law of universal gravity. Weight also equals to gravitational constant, mass of Earth, mass of the object, distance between the object and the Earth. By comparing these two equations, we can conclude that the g, which we are familiar with, which is 9.8 meters per second square, the acceleration due to gravity equals to gravitational constant times mass of Earth, radius of Earth square, being divided. Yeah. And if you put in all the numbers of those constant, gravitational constant, the mass of Earth, radius of Earth into this equation, we'll find the number 9.8 meters per second square. An object like an airplane is rarely acted by just one force. What we care about is the net force, which is a vector sum of all forces acting on it. Looking at these simple diagrams, if two forces acting in the same direction, they add up. If they add in opposite direction, they subtract, and the net force from 4 Newton to the left, 10 Newton to the right, add up to a force which is 6 Newton to the right. If they act at an angle, we use vector addition, like the Pythagorean theorem here. This is critical. When aircraft is in straight, level, unaccelerated flight, means it's at a constant velocity and a constant altitude. What's the net force acting on it? It's 0. Thrust exactly equals drag, and lift exactly equals weight. The forces are balanced.